next thing. Bayes' theorem. Bayes' theorem's your friend. So it's probably one of the most important probability, like it's one of the most important equations you can remember. It basically calculates that given the probability that something has happened, so I showed you that, given the probability that something has happened, what is the probability that something else will happen? So the way to read it is the probability that A is true given that B is true, or if you flip it over, it's the probability that B is true given that A is true. And then probability is probability of observing A and B independently. What that basically means is that it compensates for variations in population size. And so what this means is if you do have a case where you have a discrepancy, so your model, for example, might be very good at detecting different classes, but when you then turn it into the population in wild, you find that if you randomly pick a sample from a population, there's a high probability that it belongs to one class versus another. A great example is disease. If you're looking at, let's say, I don't know, HIV, you've developed a new test for HIV. The challenge is that there aren't that many people with HIV in the population. And so if your test is not really accurate, there's a risk that you will end up with, when you turn the model onto the general population, you'll actually see that it's not that accurate because overwhelmingly the model is biasing. If it guesses that its person doesn't have HIV, then it's correct, and it'll be correct most of the time. So if there's a bias in your model, then towards guessing HIV positive, then chances are like that's an issue in your model. So it needs to compensate for the fact that there are very few people with that condition in the general population. So this is one thing from Silicon Valley. So hot dog versus not hot dog. So suppose you have a model, you can basically detect two possible objects, whether it's a hot dog or whether it's not a hot dog. So if the model sees a hot dog, it can identify it correctly 99% of the time. If the model sees something that's not a hot dog, it will correctly say that it's not a hot dog 99% of the time. So suppose you have, here you have a discrepancy where you see there are only 50, so in general, in the universe, the probability of something, this is obviously wrong, but the probability that something's a hot dog is 5%. I mean, that's a very sad universe because but let's say that is in fact the case.
Great for little kids.
It would be 5% of everything around you is a hot dog. So, but hypothetically, if that's the case, so the probability is that if the model identifies something as a hot dog, then is it really a hot dog? So this is actually one of the biggest challenges in cases where where the case of something not being the case is there's an overwhelmingly like the majority of things in the world don't belong in that category, then you have a problem. So for example, we had a model that detected adult content. Well, guess what? The majority of stuff in the universe is not adult content. Well, I don't know, maybe it depends on which part of the universe. But in general. So what that basically means is that the model, when you turn it on the wild, it's not going to be as effective, simply because, and that's exactly what we saw. So even though with the training set, it was fairly highly accurate, but when you turned it into the wild, if it was adult content, it was pretty good at defining it, but if it's just general content, there were a lot of false positives. An example is that when somebody had a long nose, it would kind of identify it as something else. So, which is was okay. So that was yeah. Okay, so using Bayes' theorem, you can actually solve this problem. So the way to read it is that what is the probability that something is a hot dog, and then what you want to do is, given that it's a hot dog, what is the probability that it's going to be a positive identification? then what is the probability of it not being a hot dog, and then what is the probability of it not being a hot dog, but it still identifies it as a positive. So what this is basically is a false positive, obviously. And then this is the probability that it's a hot dog, and it's basically just the same thing as there. So then what this says is that given that your model comes back with a positive identification of something as a hot dog, what is the probability that it is really a hot dog? Right? Is that clear to everyone? Yeah. Right? So going back, so the probability that something is a hot dog in the general population is 5%. The probability that it's not a hot dog is 95%. The accuracy, if it's a hot dog, it's 99%. And if it's not a hot dog, it is 1%. That's the false positive rate. So if we work it out, it turns out that given that population distribution, the overall accuracy of my model is only 84%, which is actually probably too high given that most of the things in the world are not hot dogs. But you can see that that number is going to go steadily down. So if you really want an effective hot dog detection system, it has to be super high probability of being accurate. It has to have really high accuracy. Otherwise, in the general population, it won't work. So this is the same thing, another example. If dogs make up 70% of the population, cats make 30%. If I have this sort of like if the validation accuracy is about 83%, which basically means that if the picture is a dog, it correctly identifies it as a dog with 83% accuracy. If the picture is a cat, then it correctly identifies the cat as 83% accuracy. Then it turns out that the overall accuracy of this model, given this population, is only 68%. So that can really severely distort your, the population dynamics can severely distort the accuracy of your model. Just to say that machine learning is so simple. For regression, accuracy means something different. It's the distance between the predicted result and the actual result, so it's not really probability of it being one or the other. And so you typically look at things like the mean absolute error or the mean square error, and then another one that's used a lot is the mean absolute percentage error, and that's basically used to evaluate whether a model is good or not. So an example would be, here's an example. So here you have an outcome. So the inferred value is 0.8 and the actual value is 0.65. Outcome 2, the inferred value is 0.5, actual value is 0.65. So then the question is, okay, well, what is the MAE? The MAE is just simply the mean absolute error of these things. So it's 0.15. And then the MSE is, in this case, 0.0225. Is that a good model or not? You can calculate the MAPE for that. And you can see that if the MAPE is 0.15, so the MAE is 0.15 and the actual value is around 0.65, then it's actually not a really good result. It's almost like a 25% off the right answer. This is more challenging. So when you have the input is it's a two-dimensional value and the output is a two-dimensional value, then how do you do it? Well, what is the absolute value of the difference between two vectors? Right. So it's basically it's the Pythagoras theorem, right? So the way to calculate that, if you have multiple dimensions, exactly. So if you have, let's say, your actual outcome is, or your estimated outcome is y0 to yn, and your actual outcome is y0, yn, then what you're basically doing, if you're calculating the absolute value of the distance, or the mean absolute value, is 1 over n times the difference between y0 prime, or yk prime, minus yk. And the absolute value of the difference between that is simply, so absolute value of yk minus yk is equal to it's basically over n is so it's y. So that would be kind of that would be actually, sorry. Let's say this is not n, this is p, because you have p samples, let's say. So this is basically, what this is that you've got two vectors. So vector 1 and vector 2. And so vector 1, vector, and this is the other way around. So this vector is your estimated, this vector is your actual, and then the distance between the two of these vectors is the absolute value for that, which basically gives you which is the difference between the coordinates. It's basically the Cartesian distance between things. Make sense? So let's look at it as a real example in terms of how that would work. So you have, let's say, an input vector x. So you have, let's say, p observations. So, and then you have the estimated output. So this is what your estimator figured out. So you've got 1 as the output, and you've got yp, right? So that's your estimated output. And then your actual output is, let's say, y hat and yp hat, right? So the way this is kind of, so this is exactly what you see here. This would be like one input-output pair. And so this is the predicted output, this is the predicted output, and then this is the estimate. So what you want to do now is that given that sample, what is the mean absolute error? Well, that's basically 1 over p times the sum of the differences between y, k, which is k equals between 1 and p. So yk minus, right? And then the difference between this is that if each of these y's are, let's say, I don't know, n-dimensional, so it's basically y is an element of, this is basically what that means. Rn means it's an n-dimensional space. So it's Rn, do you know what that, so people are okay with that? Like, it basically just means that there are n dimensions to that space. And so when you calculate that, then this yk to yk becomes equals 1 over, is equal to sum of, let's say, j equals 0 to n minus 1 to, and that's going to be yk j, because this is a component of that vector, minus y hat k j, and then square that. So it's actually, I should do it that way. Oh, yeah. Anyway, so it's like.
So we never have to take the square root of anything?
Yeah, sorry, and then you have to take the square root of that. Sorry. And that's basically the norm, so taking that as the mean absolute error. And so then you just sum over that and average over the whole thing. And so in this case, then the MAE is 0.14 and the MSE is 0.02. So one way to estimate things, so if I go back, let me actually, so if I'm looking at the VIX model, let me just go back to the VIX model as an example, because that's a real example. So the VIX model is, this is your previous 5 days, next 5 days. So everything about this model looks good. You have an MAE, it's decreasing with the number of epochs. Now the question is, how good is that model? Well, you can make an estimate. So you can kind of see that, so the way to think about it is a 5-dimensional vector. And in this case, the 5-dimensional vector is each dimension is a day, right? So you've got previous 5 days, so that's a 5-dimensional vector. Next 5 days, that's a 5-dimensional vector. So you can have a rough idea of the magnitudes. And so the way I kind of think about it is when you look at what is the magnitude of this. So this is approximately, each of these is approximately 10, right? Or let's say it's like it's going to be a minimum of around 10. So which means that if you have 5 of these values, well, what you do is you can basically take, let's just make a guesstimate saying that let's say every one of those are 10. Then you take the square root of 5 because it's 5 dimensions, and the square root of 5 is 2.27, and then you multiply that by 10, and you get about 22.7 overall. So 22 by 22.7, you see that the MAE is about 1.4. So that basically means the accuracy is about 1.4 over 22.7 approximately. So it's a very accurate model. I didn't expect that, by the way, when you calculated MAE. So the way that, so this is a good way to calculate it overall, because what I've done is I've done a randomized, firstly the initial, I shuffled it initially, so that eliminates any sort of bias that I'm accidentally capturing like sequential data, and the model is just learning kind of that. I randomize it between each iteration, so every time, each epoch, I randomize it. And the fact that I got this means that there really is a signal there, and it's a really strong signal. So which means in the VIX market, there's a high probability of calculating what the next 5 days are given the previous 5 days. So whether you can make money on that, that's a different thing.